Okay. He's the Dong Professor of Epidemiology at Harvard and is well known for early work, even from the early 80s, on dynamic causal analysis and dynamic models for a doubly robust estimation and many other things. Jamie will be talking about assumption-free inference for causal effects estimated with machine learning. Welcome.
All right. Well, thanks for the invitation. And I'm going to jump right in on the story here. Oops, as soon as I figure out how to do this. Okay, so what I'm talking about is a paper actually that was just published within the last 6 months in Statistical Science, and with Wen Liu and Rajarshi Mukherjee. And it's based on earlier papers with Wen, Rajarshi, Hud van der Vaart, Eric, Chechen, Whitney Nui, who's here, and Wing Wing Wing. Okay. Okay. So first, what I'm going to do. So valid inference, by which I mean valid test and confidence intervals for causal effects, are important in many subject matter areas in medicine, which I work in. It's critical to evaluate whether a non-null treatment effect estimate could differ from zero simply because of sampling variability, especially if treatment has some toxicity. Conversely, when a non-null effect estimate is compatible with a clinically important, when a null treatment effect estimate is compatible with a clinically important effect, you want to know whether that's true, because in that case, an increase in sample size would be helpful. So in observational studies, control of confounding is a necessary condition for valid inference. And causal effects, as we'll see, are not consistently estimable without assumptions such as smoothness or sparsity, even when the effect is identified. That is, as we'll see, the bias may be of order 1, i.e. not consistent, even though the standard error of your estimator is 1 over the square root of n. So the question is, my goal here is to say, well, given that's true, what can we say without any assumptions? Is there anything to do unless you want to make assumptions that may be wrong? Okay, so this is going to be based on Skeptics' theory of statistics, which I got this way of thinking from David Friedman, if you knew. So the social norm many of our parents taught us is if you don't have anything positive to add, just don't go criticizing others. And the skeptics or curmudgeon social norm is not having anything positive to say, does not relieve you of your duty to criticize others. Or another way, it's often said, it's not what you don't know that hurts you, but what you think you know that ain't so. That requires criticism from others. Okay, so there are a bunch of new notions that are going to come up, but we can go back to them at the end. Just because of time limitations, I'm going to go right into it so you see what the problem is and what the issues are. So I'm going to do it in the context of a specific hypothetical example. So I have A, Y, and X, and I have a big data set, 10,000 to 100 million, and sample size N. IID copies, A is a binary 0-1 treatment, Y is some outcome, and X is some d-dimensional vector of baseline covariates, mixed, continuous, and discrete. And D could be very large, bigger than capital, that should be capital N. And we're interested in various causal effects. So we have observational data, but we're going to assume we've correctly assumed that nature ran a randomized trial given the covariates. That's the assumption that we're going to need to have identification, even though that's not going to give us consistent estimation. If you're a graph person that says X is a non-descendant of treatment that blocks all vector paths from A to Y. Okay, so the only difference with a true human run trial where randomization probabilities depend on the covariates is that the probability of treatment given X equal X is unknown. And that probability of treatment is called the propensity score, probably A equal 1 given x equal x to the mean of A. And I'm writing it as pi of x. So there are only two functions you're going to have to remember. One's parentheses, the propensity score, which I'm going to use pi for. Okay, and I'm going to assume that you have what's called pi positivity, that there's some constant, and with probability 1 pi is between 0 and 1 minus, between sigma and 1 minus sigma. And then we get identification, and in fact, at each level of x, association is causation. That is, if I take the mean of y in the treated given x equal x minus the mean of y in the untreated given x equal x, that's the average actual treatment effect of treatment among people who have x equals x. So this contrast in a randomized study is a causal interpretation. And we're going to only care about the observed data. So that's gamma of x is identified, obviously. If with a binary, if the treatment effect were the same at every level of x, that is gamma of x is a constant, then one way to write the average treatment effect is as the conditional covariance between y and a given x over the conditional variance of a given x. So the only other function you have to remember is b of x. That's the mean of y given x. And so the treatment effect is then the numerator, which is the expected conditional covariance between a and y given x over the denominator, the expected conditional variance of a given x. So those are okay. So people often talk about the average treatment effect rather than this particular functional. I'm going to talk about this functional because it makes all the technical discussion much easier and allows you to see what the heart of the story is. So at this moment, you can forget everything about causal effects. All we're going to talk about is inference for the numerator of this functional, okay? The expected value of y minus its regression on x times a minus its regression on x, the average of n. Okay, so again, these are the only two things you have to remember. V of x is a regression of y and x, pi of x of a and x. Okay, and so we're going to try to estimate psi. And psi is 0 under the causal null. Okay, so the state of the art estimators, I'll call them, are based on first order influence functions. So it turns out for this parameter, the first order influence function is just y minus bx times a minus pi x. That's why I'm saying it's a beautiful parameter, because you don't have to know anything fancy to get the first order influence function. And so then the state of the art estimator is to take the sample average, replacing the expectation, and plug in estimators of pi and b. So we're going to call this estimator psi hat doubly robust. And for the moment, I wanted you to think of pi hat and b hat as coming from a different sample. There's just some estimates that somebody handed you. You haven't used your data yet to estimate them. Okay, so think of them as fixed functions. So the bias, so I can actually now compute the bias of that estimator. And if you do it, it's just, so I'm looking at the bias of this guy minus the true effect, the mean of that guy minus the true effect. It's just the expectation of the error in estimating b times the error in estimating pi. Okay, and notice that this estimator has no bias. If it turned out that the estimator you had for b was equal to b, or the estimator you had for pi was equal to pi, it would have no bias, and you wouldn't have to know which of the two was right. So when you have that fact, we call that the doubly robust estimator, because you only have to get one of two of the nuisance functions in the estimator correct. Okay, and so the results I'm going to talk about here generalize to a much bigger class of doubly robust functionals, which are called mixed bias, the mixed bias class, that are have both a class at Whitney and others have looked at before, affine functionals, conditional expectations, in a class I looked at before.
Excuse me, can I interrupt and ask a question?
Yeah. Yeah.
So when do you, I'm a little confused. You said, so it's doubly robust because if you know one of them, you mean almost surely in X, then you have no bias. But do you ever hope that this will ever happen?
No. So that's who, I don't hope that'll ever happen. I'm just giving you a way to think what the definition is. If it were true that I had it exactly, you'd have no bias. In fact, you hope both B of X minus B hat of X and pi of X minus pi hat of X are small. And so maybe even though you're not estimating them at parametric rates, you're at the bias you get it to be small o p n to the minus a half.
So I'm not sure how to think about this. Is this a statement you're going to relax, which is if I know one well, then
that's definitional. Yeah.
Okay.
If all I meant, yeah, I'm gonna totally relax it. You'll see how far. I'm gonna relax it to knowing nothing about B of X or pi of X.
Okay.
Yeah, so it's a definition. If one or the other is true, you didn't know which, and you have no bias, we'll call it doubly robust. Such an estimator is called doubly robust, not it itself. You don't have those things, so you're not in such a good position. But okay. So our goals these days, often pi of X and B of X, the estimates will be estimated by machine learning. Still think about it in a different sample. So all doubly robust estimators, by definition, have second order bias. That is, they're a product of biases in the error of 1, B, and pi. So it's small if pi, either pi small or B small, and it's very small if they're both small, because you get this product smaller. Okay, remember, okay. So people use machine learning algorithms usually because they're better at estimating expectations than parametric models, kernel smoothing or polynomials in X when the sample size is, they do better than the things we used to do when the sample size is large, like, deep neural networks or something. Okay, so the functions pi hat and b hat of X are returned by black box arbitrary ML programs. And they generally have, at this point in history, complex unknown statistical properties. So how can we use them and still get valid tests and confidence intervals? That's a hard enough problem, but even more, I don't want to even assume the true B and the true pi are non-complex. I don't want to make smoothness or sparsity assumptions. So I'm using unknown black box to estimate them, and I make no assumptions about them. So what can we do? Okay, so we're going to need one other. So we're going to need one other idea, which is sample splitting. So we're going to talk about how where we estimate B and pi from, and we're going to actually split the sample so that the estimator I was showing you, we're going to compute on one half of the sample, but the functions, B hat of little x, pi hat of X, the functions we're going to estimate on the other half of the sample, and that thereby avoiding problems with correlation between the estimated B and pi's and the random variables in our sample average that was our estimator, psi hat dr. So then we don't need Donsker conditions and so forth because we're making no assumptions about these guys or about their estimators. We don't want to rely on things that need assumptions. So I'm now going to define the following state-of-the-art estimator. So this is the algorithm that is now, let's say, state-of-the-art. The n study subjects are randomly split into two parts, an estimation sample of size n and a training, or better probably call it a nuisance sample of size and training. Let's make them each about half the sample. And we construct the estimators B hat and pi hat from the training sample using ML method estimators. And then we compute the doubly robust estimator from the data in the other half of the sample. Remember, n, I1 to n is the first half of the sample. using those estimates b hat and pi hat, but evaluated at the data in the sample we're using for computing DR. And people don't like throwing away half the data, so then they do something called cross-fitting, where they reverse the training estimation sample and get the doubly robust estimator they would have gotten if they had reversed them and then averaged the two. So for better or for worse, these are the standard, let's say, state-of-the-art things people are doing these days, okay? So the following theorem gives asymptotic properties of psi hat dr. So first, conditional on the training sample. So I'm only thinking of dr, not the CrossFit guy. So conditional on training sample, it's asymptotically normal because it's the sum of IID random variables. Conditional on the training sample. And its standard errors order n to the minus a half because it's the sum of IID random variables. And it's got bias, what I showed you before, which is right as an integral because I'm treating b hat and pi hat as fixed. That's the bias. Okay, so, and notice that the bias is only random through the training sample, right? It's through b hat and pi hat. Okay, and so what we mean, and if the bias was small op under the minus 1/2, it means that the conditional bias becomes negligible compared to the standard error. Notice that you have a change. Remember, b of x, pi of x, we've estimated some non-parametric method. So for b of x minus b hat of x alone, you wouldn't think it was small, op under the minus 1/2, because that's parametric rates. But because it's doubly robust, the bias is a product, so we might be okay and have the small bias.
Excuse me, can I ask a dumb question? Sorry. So
yeah.
So what if my ML, so I don't understand, where is the assumption on that ML algorithm works? Suppose my ML algorithm outputs b hat equals 0 and pi hat equals 0.
Yeah.
So how can you get this this first bullet?
I didn't say we could get it. I was just saying what it would mean. Yeah, I'm just sort of telling you the state of the art, how people think. So they hope it's this. They don't, people who usually do this, what they do is they use some ML algorithm and then they make some high level assumptions that shows under those assumptions for both about sparsity or smoothness and maybe something about the properties of the ML algorithm that this will be true. But they'll do it by fiat because they want valid confidence intervals centered at their estimator. And that's exactly my point. The discussion here is going to be, what can you say if you won't make any of those assumptions? So you can think of, I'm showing you the straw man so far that I'm going to critique, okay? So I'm not making these assumptions. I'm just telling you, that could be true under certain smoothness assumptions, or if you use certain estimators of certain kind of machine learning estimators. So for example, if you picked among machine learning estimators, you fit a lot of machine learning algorithms, including just using, series regression with wavelets. And if I told you that pi and b lived in certain holder classes, then you could say, oh, well, my final estimate of pi hat and b hat, we might have this property if they were sufficiently smooth, because by cross-validation, we'll get an error, L2 error less than better than the worst, better than any of the ML algorithms I'm looking at. And if one of them's just wavelet regression, we know that's kind of optimal for estimating smoothness classes, so that if you have enough derivatives in B and pi, that assumption is correct, and you use the right estimators, as I just described, you will satisfy this. So the issue is really that we don't know the smoothness assumption is true, or sparsity, if you like that. Okay, so okay, so now if we look now on if we, so people in general, the thing I'm going to criticize is the unconditional view of this, even stronger. So that if in fact the bias is OPM to the -1/2, and B hat and pi hat converge to fixed functions, the truth and mean square, then this estimator, our estimator times n to the -1/2, the error, converges conditionally and unconditionally to a normal with mean 0. And the cross fit converges unconditionally to a normal distribution with mean 0 and variance equal to the semi-parametric variance bound for estimating our functional psi. Furthermore, the nominal 1 minus alpha wall the intervals, we take the estimator and add, z alpha over 2 times the standard error, or an estimate, a consistent estimate of standard error. There'll be valid 1 minus alpha asymptotic confidence intervals for psi. So that is the paradigm. So people assume they have this condition and all the conditions necessary to make their confidence intervals valid, and that's the standard move. They use the estimator, they say we have enough smoothness or sparsity and the right estimators of the nuisance parameters to give us valid asymptotic confidence intervals. So the point is, for this talk, that's a minor interest to us, because without sparseness or smooth or sparsity assumptions that might not hold, we can't guarantee the small bias. And less important, B hat and X and pi hat of X have unknown properties. And since I don't believe these assumptions necessarily, I'm interested in assumption-free inference, no smoothness or sparsity assumptions, unlike in the usual literature. But if you assume essentially nothing, what can be said? Well, nothing, because even a consistent estimator over the model where I make no assumptions about B and pi, other than, let's say, having, bounded away from 0 and 1, having finite moments, you can't say anything. You can't guarantee consistency. Further, in a certain sense, it's not possible to test the biases of this order either, because that's an asymptotic statement that that's not clear exactly what you're testing there. So we're not interested in the usual analysis. What we're interested in is questions like at the finite sample size n we really have is the actual cover under the particular law generating the data, coverage of the parameter of our walled interval, as reported in a published paper. So I've just read a published paper, they give me this interval, it reports a coverage of 1 minus alpha, because it made all those assumptions, which I don't believe. And I question, I want to know, does it really cover at 1 minus alpha? Or can I show that it doesn't, can I use the data to show that the coverage, whatever, at the true law is no more than, let's say, 20.27 when they say the coverage is 90%, okay? So the idea is I can't, this is the skeptic. There's no way I'm going to say anything positive if I make no assumptions. But I'm going to show you I may have enough information to show people who have made the assumptions are wrong and criticize them, and even sometimes tell them, give them an upper bound based on the empirical data of what their coverage actually is, even though they claim 90% coverage under their assumptions. So the goal here is to criticize the state of the art because I'm making no assumptions. And so I can't say anything positive because I can't get consistent estimation with no assumptions, even though I have identification. So, so because of that, because that's my goal, I'm going to regard the training sample as fixed rather than random. Because I'm not going to make any assumptions about the conditional bias, even probabilistically, because I'm not going to make any assumptions about pi and b, so I might as well just choose them as fixed, treat them as fixed functions. So the only randomness to me is in the estimation sample, where I'm doing a sum of IID random variables. So the inference I'm going to make are going to only rely on being an asymptote, only to posit that our sample size n in the estimation sample, the quantiles of the finite sample distribution of the estimator minus its expectation is near to a normal. I could use finite sample inequalities at the cost of somewhat less precise results and make, no assumptions. But it turns out all the simulations we do and so forth, our sample sizes are big enough so that conditional on the training sample, this guy, looks exactly like a normal. So I'll use normal quantiles, but the only randomness is from the sum of IID random variables. I'm fixing pi hat, b hat, because I don't know anything about them. Okay. So we may fail to estimate these guys sufficiently well, no matter what machine learning program we use. But how do I then judge whether the confidence interval people are giving based on the state-of-the-art method I just showed you with sample splitting and so forth? How do I know how their coverage is doing? Okay, so this week's the question: can tests be developed in the ability to detect whether the bias of this estimator is of the same or greater order than its standard error of order n to the minus 1/2? So that, because if that's true, the nominal walled intervals will undercover. If yes, if I can test that, and I show that they undercover, my test rejects, can we construct new estimators that are less biased? And can I do this without refitting, modifying, or even having knowledge of the ML algorithms that are employed, and without requiring any assumptions at all, aside from a few standard weak assumptions we'll talk about, in particular, without making any assumptions about the smoothness or sparsity or function class of the true outcome regression or propensity score function? So to construct my test, I'm going to need data. I'm going to need the data from the study, the same data the analysts used, and I'm going to need the functions b hat and pi hat outputted by their machine learning programs for the two regressions. But I don't need to know what programs they used. I just need to know their b hat and pi hat. So okay. So I'm going to show you, given that, I'm going to be able to construct a test that can show that they're reject the hypothesis that they have coverage of 1 minus alpha that they claim. And the key is going to be an unbiased estimator of part of the bias. Remember, this is the bias. I'm going to show you there's no way I can estimate that bias. That's why I can't be consistent, because it can always be order 1, given my assumptions, which are essentially none. But I'm going to be able to estimate a part of the bias without many assumptions, and using a second order U statistic. And that depends on a theory of higher order influence function. In the second order U statistic, I'm going to index by K. I'm going to tell you a bunch of things it depends on. So it's going to depend on an index K, where the higher the K, the better. But I'm going to need, for reasons I explained, K less than the sample size of the estimation sample. And I'm going to take my original estimator, and I'm going to subtract off my estimate of part of the bias. I know I can't estimate all the bias. And so my bias-corrected estimator, I would like to show, is better than the original estimator, even though my bias-corrected estimator may be inconsistent. I may be able to show you the bias is less than the original estimator. And if I can do that, I can show you that the original confidence intervals fail to cover, as you'll see. So how can so I want to explain what the statistic is and how and in what conditions I can say that I've constructed an estimator with smaller bias than the original state-of-the-art estimator. Okay, so this statistic is a second order U statistic that depends on a choice of k basis functions. So Z1 through Zk of functions of the high dimensional vector of confounders. For the moment, there's a lot of open questions, as we'll get to at the end, of how to choose this basis. But the results I'm going to give are going to be true for any basis you choose. But if you choose a bad basis, your test won't have a lot of power to reject the hypothesis that reject their hypothesis that they're covering correctly. But for the moment, you can choose any way you want k less than n basis functions. And you might have picked good ones or bad ones. I'm going to tell you the procedure I'm going to use once you hand me these basis functions. Okay, so I'm going to use this symbol for the inverse of the expected outer product. I'll call that the covariance matrix. This is the inverse of the expected outer product of the ZKs. And I'm going to let pi hat of that be an empirical estimator, pi hat omega. And in practice, K and the estimator we choose adaptively. And the bigger K is, in principle, the better. It's got to be less than n for reasons I'll say in a moment. If we want to make no assumptions on the inverse covariance matrix, such as itself, such as sparsity, because I want to make no assumptions. So I don't want to use a covariance estimator that I need to justify its properties based on such assumptions. And therefore, I better choose k less than n, so I can always use the empirical covariance, the inverse of the empirical covariance estimator. So we actually have some estimators, so I'm going to go, that do better than the empirical covariance estimator. But the empirical covariance estimator, the theoretical results for it are very good. It's just they don't do necessarily so well in middle-sized samples. So today, what I'm going to do is I'm going to assume we have semi-supervised data. That is, you have a lot more data on the x's, a lot more bigger sample on the x's than you do on the a's and y's, the treatment and the outcome, so that we can treat the covariance matrix as known. This is going to make it much cleaner and you're going to be able to understand it. But the point is here, at least for the theory, if it's unknown, but k is less than n, and I use the inverse of the empirical covariance matrix, and we have certain, usual assumptions on, the smallest eigenvalue and so forth, that we get essentially the same results. But the things are much more complicated. The estimators, I have to use mth order U statistics for large M rather than second order. So here I'm going to do the results as if I know the covariance matrix of the x's, of the z's, of the zk of x's. But the results, that's not the key to the results. I can get essentially the same results if I use the empirical estimator.
I have a question about this.
Yeah.
So it's hard for me to foresee what you're going to do, but if you're going to construct other estimators beyond this omega inverse. But if you were to, would you need some sample splitting if you were to not assume that this omega inverse is known? Would you need
I still need sample
split?
Yeah, I still need sample splitting to estimate d, the mean of y given x, and pi, the mean of a given x. So I use the sample splitting for that. If I had to also estimate omega inverse by the empirical inverse covariance matrix, because k is less than n, I would also use that other sample. Okay.
Okay, and throw the y's for this guy.
And do what?
And
Sorry.
throw the responses for this guys. You would only keep the X's, right?
Yeah, so yeah, to estimate this guy, so I
Yeah.
split the sample. For this
In three,
guy,
that would be
use
in three
half-
parts.
Yes, but I can do all three. I can do three of the parts. I can do all the things I don't know, complicated object, all
Okay.
in half the sample at the same time. The B,
Okay.
the pi, and this guy. And then I move them back into the other sample because I'm going to show you an estimator that requires this guy or an estimate.
Okay.
And I'm going to do that on the estimation sample.
Thank you.
Okay, so the amount of bias corrected and the improved coverage of my bias corrected estimator side 2, K, depends on the number of bases, which bases they are, what functions of X, and my estimator there, which the purpose of this, you can think of that as just the empirical, but I'm going to assume we know it today. Okay, and how do I choose Z? Well, there are a lot of ways. Like I could just do agree. One way to think about it is I could well, there are a bunch of ways, like using lasso paths and greedy maximization. I'll show you when I get to the statistics. But the point is, we don't have, part of the reasons I'm not going into that is that's a second issue, but also we don't have a solution to it. It's an open problem, how to get good Z's. But what I'm showing you today is true for any choice of Z's. Okay, so now I'm going to show you the part of the bias we're going to estimate. So it's not, okay, so consider B, the error in estimating B. Okay, I'm going to take the least squares and consider the least squares projection of this error, B minus B hat, on my K basis functions. So I'll write that as the projection of B minus B hat on, this means the space spanned by my K basis functions. And that's just least squares, so it's beta times zki of X, and beta is the expected value of Bx minus B hat X, zk transpose times the inverse of the outer product matrix, which I'm going to assume is known. And this is also equal to the expectation of Y minus beta hat X, zk times that, because conditional on X, the mean of this, by condition on X, this Y becomes B. So if I know this guy, so I know this guy, I know Y, because that's my data. You know, I know these guys, and I have Xi in the estimation sample, and I know this guy because that I took, you know, you inputted that to me. That was what the machine learning guy gave me. And I can replace this expectation by a sample average. So you see, I'm going to be able to get an unbiased estimate of this guy. So, so what I really want, the part of the bias I'm going to estimate is the expected value of the projection of the error in B on those guys times the projection of the error in pi on the ZKs. So given what I just showed you, if you write it all out, you can see that substituting in what I showed you, this thing turns out to be just the mean of Y minus B hat, i.e. the residual, times ZK times the inverse, expected value ZK transpose inverse, times the same thing with A minus its residual. So the thing, okay, and this I have an unbiased estimator of. I just use a U statistic where for a person, I know this, so I put it in the middle. This guy is unbiased for for beta BT, okay, and this guy is similarly biased, unbiased clearly for this guy. So this whole thing is an unbiased estimator of this, and that's part of the bias in particular. So I have an unbiased estimator, second order U statistic, I need a U statistic because I want an unbiased estimator of this guy, and I have an unbiased estimator of this guy, and I have an unbiased estimator of this guy. So to get an unbiased estimator of their product, I have to use a U statistic. So I have two independent things. So when I take the expectation of this, I get the expectation of this guy times the expectation of that guy, which is why I need a U statistic. Okay, so this estimator, what are its properties? Okay, so it's an estimator of this part of the bias. Its properties are the following. Okay, so it's this U statistic, and that's its kernel. Its standard error turns out to be the square root of k. That's the number of dimension, the number of covariates. I have the number of basis functions over n, which notice is less than 1 over n to the half. So this guy actually has smaller sampling variability than 1 over the square root of n. So since the standard error of my double of psi hat dr is the sum of IIDs is n to the 1 over n to the half, my new IF22 has a smaller sampling variability than this guy. Okay, so k less than n means that my partial bias corrected confidence intervals. So remember, I'm going to take my original estimator and subtract off IF22. I'm going to have length approximately equal to the original walled intervals centered at C hat dr, because I'm adding a term whose size is going to over the size of this. This has less variability, so it will add a vanishingly, in large samples, it'll add a vanishingly small amount of variance. It also means it's possible to detect for any delta greater than 0 that the ratio of the part of the bias of psi dr I'm estimating to the standard error of psi dr exceeds delta. So I'm trying to, so what I'm saying is I have something that's order n to the minus 1/2, and I want to see the standard error, and I want to be able to detect error, that the bias of my estimator is greater than that standard error. And I can do it at the exact same order as that standard error, which may seem surprising because we often think we can't estimate things at faster rates than 1 over the square root of n. But because because the guy I'm moving the bias by itself has smaller than 1 over the square root of n standard error, I will be able to test such hypotheses. That is, for any delta, it's possible that I can detect with probability going to 1 as n gets large, whether the part of the bias I've been talking about exceeds delta over the square root of n, even though, which is better than we usually think of. So what's the relationship to the part of the bias to the total bias? Well, remember, the total bias, so I'll call that C bias, is the expectation of the error in B times the error in pi. But by the Pythagorean theorem, or its equivalent, I can write that as the expected value of the product of the projections of these two things on the z's plus the projections onto the orthogonal complements. But this part, that's my part of the bias, I have an unbiased estimator of. This I know, I can estimate. It's just the expected value of IF22, right? That's what IF22 is. And this part of the bias, I can't estimate because this has an infinite number of terms. Because it's from k to infinity. I'm doing an expansion at a basis, right? I only have k less than n. So if I tried to do my same trick to unbiasedly estimate this guy, k would have to be infinity, which would mean I can't do it consistently. And it's because I can't estimate the tail consistently, that part of the bias, that I can never be sure. I can have a consistent estimator of my parameter because I'm not making any assumption any assumptions at all about the B's or the B hats. So I have no assumption that the tails here are small. I have no way to say that. And that's why with no assumptions, one way to think of it is you can't get consistency for estimating psi. And why even my bias corrected estimator, I can't say it's consistent because I always subtracted off this part of the bias that I was able to estimate. But it does mean I can at least estimate part of the bias. Okay, so that's what I'm saying here. I can never rule out that their bias is order 1, much less 1/n². Now, let's take the special case where I make A equal to Y. That was actually the denominator. If I make A equal Y, it's got my procedure has some particularly nice properties that I'm going to explain. So if A equals Y, my parameter becomes the expected conditional variance of A given X. This guy, where B and pi are now the same, B hat and pi hat are now the same, because I'm just doing this example now. Then I know that this guy has smaller bias than my original guy, because both pieces of the bias of psi 2k inverse, both pieces of the bias I showed before, these are the pieces of the bias, remember, this guy and this guy are both positive, because if I put B here also, because I'm doing this B equal pi, these are squares. So I know with certainty my estimator has improved upon the bias of the standard guy. And we've also seen I haven't increased the standard error, at least asymptotic. I've increased it by, less than 1 over the square root of n. So this is a better estimator if I'm doing the variance. Okay, so this guy is smaller bias. So the previous statements now are true of the entire bias, not just part of the bias. That is, I can detect now whether I can detect sometimes whether the bias of theta, the real estimator, exceeds its standard error, because if the bias of the part I can estimate exceeds its standard error, then I know the whole bias does, because the other part of the bias has the same sign as the part of the bias I estimated when I'm estimating the variance functional. Okay, so I can do this very sensitive test. But even for this functional, test of the null hypothesis that the conditional bias of the DRML estimator is much less than, say, 10% of its standard error will not be a consistent test, because it might be that the part of the bias I can estimate, I estimate to be 0. So so if the part of the bias I'm estimating, I have a bad choice of the ZKs, so the projection on it of the real bias on the ZKs is small, then I won't know that the real bias, the part I can't estimate from K on, is large. So I'm able to reject the hypothesis if the part I can estimate, I can show the mean of IF22 is greater, some fraction of the sample size, is order 1 over the square root of n. It increases it's not small compared to the standard error. But if it fails to reject, so if I have a small p-value for my for testing whether IF22 is 0, I'll have good evidence that the nominal 1 minus alpha confidence interval of the standard estimator undercovers. I can falsify that because I've shown my bias corrected estimator. The correction of the bias is more than 1 over the square root of n, or a significant fraction of the of the standard error of the original estimator. Therefore, the original estimator could not have been centered on the truth. But when the test does not reject, we cannot conclude there is good evidence for the null hypothesis, because no matter how large the sample size, I never know what's going on in the tails, because I'm not making any complexity reducing assumptions that would tell me the tails are small, the projection on the tails. Okay, so no test can be consistent without making additional assumptions that may be incorrect about the true but unknown propensity scores. So what can we say assumption free? We can criticize, falsify, and improve if we can criticize, falsify the previous confidence intervals, give improved confidence intervals, but we cannot guarantee an improved estimate with less bias. We cannot guarantee correct coverage with interval length decreasing the sample size. That is, we can't get consistency. We can't get a confidence interval that gets smaller with increasing sample size and still is correct. Okay, so that's my point. There's not anything to say positive. We can't say anything positive, but we can criticize. Now, if A and Y are different, going back to the expected conditional covariance, we can say even less. And that requires some new philosophical ways of thinking. But at this point, I'm hoping you have the idea. So at this point, if I was just doing the variance, I would say always use my estimator side too. It's always better. It's always got less bias. Its standard error isn't really very different. And therefore, there's a chance its real bias, its real bias is that tail term, is smaller than the standard error. I can't prove that, but I always do better than the initial guy. So the state-of-the-art estimator should be side 2. But that required, now here's the subtle part, that required A and Y being the same variable. So I knew the two parts of the bias were in the same direction. The part I could estimate and the part I couldn't. So, okay, so what does this all look like? Suppose you read a paper. So this is what it's all for. I mean, so I would like people to really use this. So here's the experience. You read somebody's paper, and it reports a 90% interval with sample, and they had a sample size of 2,500 in both their estimation and training sample. And they say, my estimator plus 1.74 standard errors. This is what they, is very significant. 6 standard errors significant. And they think they report they really know where this parameter is, and it differs from 0 and so forth. But I take their data, their estimation sample, and their B hat and P hat, and I compute my psi hat 2, remember, which is just their estimator minus my unbiased estimator, IF22, of the of part of the bias. And when I do that, my estimator is 0.006 plus 1.64 times a slightly bigger standard error, because I have added a term, but it's not double the standard error. But look how much I've changed the estimate of the bias. This means that since if I'm doing the variance, their bias was at least, forgetting sampling variability, 1.97, 1.91, 0.191 too high. And in fact, the bias could easily, psi hat 2K is easily consistent with 0. So I know the confidence interval they gave here was massively under covering. It probably had coverage near 0 because they thought they were sick. They put, a standard error around something that was 6 times bigger than it should have been, okay, because of this bias. And I've been able to estimate the bias because the part of the bias I could estimate was large. So, okay, so this guy has bias 6 times its standard error. So you can see its coverage is going to be 0, okay, of its confidence interval, because its bias is, okay, of its Wald interval. And similarly, I could do a test of whether, statistically, I would do a test of like whether the mean of IF22 over the standard error of the guy I'm interested in, let's say is less than 0.3. I'll choose some number. And if the test rejects, I can tell you something about how much they must have undercovered by. So I can either do it by estimation or testing, is what I'm saying. I can test this hypothesis, because if they have correct coverage, they better not reject this hypothesis. That they better not reject this one. This is 0.1, 0.05, because they have to have their bias negligible compared to the standard error. So I reject this hypothesis, which I can because I've done a bias estimate of this and I have a good estimate of this just by using this statistic numerator. Remember, I have this estimator minus that, minus 0.3, and get its standard error of this guy of IF22, which is small. And so I can do a test that also tells you they've undercovered. And these were actually drawn from simulation. And in that simulation we did, in fact, since I knew what was going on, these things are true. If you use in the simulation, the usual guy is biased upwards by 6 standard errors. But psi hat 2K was actually unbiased, but I'm cheating. I could have done a simulation where there was the bias, part of the bias, the tail bias I couldn't estimate was large. And then we both would have undercovered, but I would have still proved he undercovered. I can't prove I myself undercovered because I don't have somebody to compare myself with. But I know this was a better estimator, and therefore this guy undercovered because I was able to estimate the bias, part of the bias of this guy precisely, and it was 0.191. That was just 6 standard errors. Okay, that was the point. Okay. All right. Okay, so, and remember, if I find that if I estimate no bias, so my estimate, IF22, my U statistic is 0. So my estimator and the original estimator are the same because my estimator was 0. My ZK didn't do anything. That does not mean no bias, just that we haven't detected anything, because I never know about the tails. All I'm doing is criticizing and possibly improving. Okay, now, so what time is it now? Does anyone know?
12:02.
Oh, so that's already when I'm supposed to finish. Okay, so I will then start. So the other part is when you're, just so I explain it, when you're estimating expected conditional covariance, the part of the bias I can't estimate and the part I can, which is can have different signs. So I can never say my estimator's better for sure, has less bias than the original estimator, because I may know that the original estimator I may have shown that part of the bias was not negligible, but the total bias might go in the other direction. So the question is, what do I do in that case? And just to sum up the whole thing, what I can do is people usually justify that the bias is small, using smoothness or sparsity assumptions. And then they prove that under those smoothness and sparsity assumptions, they prove by Cauchy-Schwarz, because they can get the expected value of the square of this guy. They use Cauchy-Schwarz, plus they prove that under the smoothness assumption, Cauchy-Schwarz says that the Cauchy-Schwarz upper bound is small o n to the -1/2, and therefore their bias is small o n to the -1/2. So if I could prove to them empirically that their Cauchy-Schwarz upper bound, the right side of the Cauchy-Schwarz inequality, is greater than n to the -1/2, then I would have falsified their assumptions upon which they justify their interval for the conditional covariance. In fact, I would have falsified their smoothness or sparsity assumptions, whatever assumptions they made, to prove that the Cauchy-Schwarz upper bound for the mean of b minus b hat pi minus pi hat was small o n to the -1/2. I would, if I could falsify that, those assumptions, I falsified the basis of their whole argument. And I can falsify just the way I did with the variance. The Cauchy-Schwarz upper bound is positive functional. That is, the part of the bias and part I don't estimate have to go in the same direction. And that's because the Cauchy-Schwarz upper bound, the Cauchy-Schwarz bias, is a product of two biases like I just was looking at for the variance. And so this guy I can prove to you, I can prove to them is not small O minus 1/2, which means I ruled out their sparsity or whatever regularization assumptions they made, and therefore ruled out the justification for their coverage of their confidence interval whenever I can use IF22 to rule out that this guy is small. If I can show it's by my test that it's greater than n minus a half. So that's the way I deal with things like expected conditional covariance, where the bias I can estimate, not estimate, don't necessarily go in the same direction. I then attack the Cauchy-Schwarz upper bound that they use to justify why they think the confidence intervals work. And that guy I can prove with part of my bias. I can use part of my bias to show the Cauchy-Schwarz upper bounds greater than the standard error of their of psi hat dr that is greater than n to minus a half. Okay, so I didn't really have time to go through that part carefully, but that's the idea. And so I'll leave it at there. So the point is, if somebody shows, so the bottom line, you go to any paper, you read it, they say, here's the confidence interval based on these state-of-the-art things. And the goal is to take that, say, we have your data and your b hat and pi hat, and then to do these tests of whether the part of the bias that I can estimate with IF22 is greater than the standard error of their estimate of the standard error of psi hat dr, the state-of-the-art estimator. And if it is, I can tell them they're for sure they're undercovering. And in fact, I can give them in the quadratic case, like expected conditional variant, I can give them an upper bound for their coverage. Okay, I'll stop there.
Great. Thanks, Jamie. Questions?